Historically, the field of mathematics has traditionally served one primary purpose: calculating physical quantities, magnitudes, and highly precise measurements. But there is a different application for math. We can strip away the numbers and use it to calculate whether a statement of human logic is absolutely true or false. This specific pursuit led British mathematician George Boole to publish The Mathematical Analysis of Logic in 1847. To make this system work, Boole removed the standard rules of algebra. This framework has no negative numbers and no fractions. It also functions without square roots, logarithms, or standard geometry. By restricting mathematical states to binary truth values, Boole built a conceptual framework that would eventually map onto the physical behavior of electronic circuitry. This photograph shows Queen's College in Ireland, where Boole served as a professor of mathematics. He reached this position as a self-taught scholar, overcoming a background of poverty and limited formal schooling. He was driven by a single goal: to demonstrate that human reasoning follows a strict mathematical structure. Because this system focuses on absolute truth, it ignores standard arithmetic operations like subtraction, division, or calculating the least common multiple. Boolean logic does not solve for numerical values. It evaluates the relationships between statements. In 1854, Boole published an investigation of the laws of thought, turning these concepts into a permanent academic discipline. He proved that mathematics is a tool for structuring ideas, not just a language for numbers. The foundation of Boolean algebra is two-value logic. In this system, intermediate states do not exist. Every calculation relies on the Boolean constant, limited to 0 for false and 1 for true. We also use Boolean variables. Placeholders like A or B can change based on conditions, but are physically forced to hold only a 0 or 1. This binary limitation changes how we handle addition, specifically the equation 1 plus 1. In standard algebra, 1 plus 1 equals 2, but in Boolean logic, 1 plus 1 equals 1. A true condition combined with another true condition simply results in true. In engineering, this mathematical 1 represents a high-voltage state, while the 0 represents a low-voltage state. By ignoring magnitude and focusing on binary states, Boolean algebra mirrors the physical behavior of an electrical switch being on or off. The first fundamental operation is the OR gate, which manages logical addition. Under the OR rule, the final output is true if at least one of the inputs is true. This explains why an input of 1 and 1 results in an output of 1. The second operation is the AND gate, which handles logical multiplication. Following the rules of multiplication, the AND gate only outputs true if all inputs are also true. The third operation is the NOT gate, which creates the Boolean complement. The complement reverses the input state. If variable A is a 1, it passes through the NOT gate and flips instantly to a 0. Every complex digital process, from simple calculators to artificial intelligence, is built by chaining millions of these three operations together. This system also contains the duality principle, a symmetrical feature unique to Boolean algebra. In this valid Boolean equation, 1 plus 0 equals 1, the first rule of duality is to swap every addition sign for a multiplication sign. Simultaneously, we must swap the constants, changing every 1 to a 0 and every 0 to a 1. The original statement has now morphed into a new equation: 0 multiplied by 1 equals 0. Logically, this new version is also mathematically true. Hardware designers use this principle to rewrite the logic of a circuit using different gates without changing the final output. By applying duality alongside commutative and associative laws, engineers can optimize massive logic architectures into smaller physical spaces. This system provides a mathematical method for evaluating truth while acting as a practical tool for compressing and perfecting hardware design. George Boole died in 1864, decades before his math was applied to any physical technology. In 1937, MIT researcher Claude Shannon, seen here in front of complex computer wiring, identified the physical application for Boole's work. Shannon realized that Boolean true-false logic mathematically mirrors the open and closed states of electronic switches. Early engineers used this logic to route physical electricity through massive arrays of wires and logic jacks, as seen in this photograph. This close-up of vacuum tubes shows the physical reality of these early high and low voltage states before they transitioned into modern solid-state components. Shannon provided the physical mechanism for Boole's mathematical philosophy, starting the digital electronic age. Today, this binary logic governs the billions of microscopic transistors embedded inside the modern microprocessors seen in this image. Engineers now use hardware description languages, built on Boolean rules, to map out these transistor layouts. The arithmetic logic unit, which functions as the brain of the computer, relies on this logic to execute software instructions. This logic also controls software processes like error detection, network data compression, and the if-else statements used in programming. This binary math is the absolute fundamental requirement for modern mobile networks, digital watches, and artificial intelligence to function. By mathematically defining the structure of human thought, George Boole provided the binary foundation used to build almost every digital device in existence.